Welcome to Chapter 3, Complex Numbers. Complex numbers expand our number system by including solutions to certain equations that can't be solved using just real numbers. A complex number has a real part and an imaginary part, and is usually shown as a plus by. Here, a is the real part, b is the imaginary part, and I is the imaginary unit, defined by the equation I2 equals -1. These numbers are essential in many fields such as mathematics, engineering, and physics. They help solve polynomial equations with no real solutions, model alternating currents in electrical engineering, analyze wave motions in physics, and contribute to areas like complex analysis and number theory in mathematics. The main goal of using complex numbers is to deepen and broaden mathematical theories and provide strong solutions to problems that are too complex for real numbers alone. A complex number includes both a real part and an imaginary part, usually shown as a plus by. In this expression, a and b are real numbers, and I is the imaginary unit, where I squared equals -1. Exploring the components. A, the real part of the complex number, shown on a horizontal line in the complex plane. B, the imaginary part, displayed on a vertical line crossing the horizontal real number axis. I, the imaginary unit, equal to the square root of -1, crucial for defining the imaginary elements of complex numbers. Consider the complex number 3 plus 2i, where 3 is the real part and 2i is the imaginary part. Complex numbers are essential for expressing values with both real and imaginary parts. They are widely used in various fields. For example, they are crucial in solving polynomial equations that lack real solutions, in electrical engineering to analyze alternating currents, in physics for studying wave actions, and in mathematics for complex analysis, enhancing our grasp of many theoretical ideas. Understanding I's powers. The powers of I, or the imaginary unit, are part of a repeating cycle. To understand it, consider this sequence: I0 is 1, I1 is I2 is -1, I3 is I, and I4 is back to 1. This pattern repeats every 4 numbers. It starts because I is the square root of -1, making I2 equal to -1. Each time I is raised to a power, it follows this predictable cycle. This knowledge is key in working with complex numbers and advancing in math. What is a complex number? A complex number combines a real number with an imaginary number. It's written as z equals a plus by. Here, a is the real part, and by is the imaginary part. When you work with complex numbers, adding and subtracting them is similar to combining like terms in algebra. You handle the real and imaginary parts separately. For example, with two complex numbers like a plus by and c plus di, adding or subtracting them is straightforward. Simply combine their real parts and their imaginary parts on their own. For addition, use the formula a plus by plus c plus di equals a plus c plus b plus d I. For subtraction, it looks like this: a plus by c plus di equals ac plus bd I. Let's use a real-life example. Add the complex numbers 3 plus 2i and 5 minus 4i. Using the addition formula, you get 3 plus 2i plus 5 minus 4i equals 3 plus 5 plus 2 minus 4, I equals 8 minus 2i. For subtraction, with the same numbers, it goes like this: 3 plus 2i, 5 minus 4i equals 3 minus 5 plus 2 plus 4, I equals -2 plus 6i. So, the steps for both addition and subtraction of complex numbers involve treating the real and imaginary parts separately and doing the arithmetic operations independently, ensuring the process is clear and precise. Let's explore operations with complex numbers. When we add the complex numbers 2 plus 3i and 4 minus 5i, the calculation is 2 plus 3i plus 4 minus 5i equals 2 plus 4 plus 3 minus 5, I equals 6 minus 2i. When subtracting the numbers 5 plus 2i from 3 minus 4i, it results in 5 plus 2i minus 3 minus 4i equals 5 minus 3, plus 2 plus 4, I equals 2 plus 6i. To multiply complex numbers, start by distributing each term of one complex number into the terms of the other complex number, then simplify. Let's look at an example by multiplying two complex numbers. Take the complex numbers 2 plus 3i and 4 minus 5i. Start by distributing each term from the first complex number, 2 plus 3i, across each term of the second complex number, 4 minus 5i. 2 plus 3i times 4 minus 5i equals 2 times 4 minus 5i plus 3i times 4 minus 5i equals 8 minus 10i plus 12i minus 15i2. Remember that i2 equals minus 1. Keeping this in mind, we simplify the term 15i2 to minus 15. Equals 8 minus 10i plus 12i 15, minus 1, equals 8 minus 10i plus 12i plus 15 equals 23 plus 2i. Thus, the result of multiplying the complex numbers 2 plus 3i and 4 minus 5i is 23 plus 2i, showing how distribution and simplification help in solving the multiplication of complex numbers. To multiply the complex numbers 2 plus I and 3 to 2i, start by distributing each part, 2 plus I times 3 minus 2i equals 2 times 3 to 2 times 2i plus I times 3i times 2i. Simplifying gives 6 to 4i plus 3i 2i squared. Since I squared is minus 1, replace and the equation becomes 6 to 4i plus 3i plus 2. Combine similar terms to get 8 to 1i. Consider this example. Divide the complex number 3 plus 2i by 1 minus I. Start by finding the conjugate of 1 minus I, which is 1 plus I. Then, multiply both the numerator and denominator by the conjugate, 1 plus I. After performing the multiplication and simplifying, we get the final expression as 1 plus 5i over 2. By the conjugate of the denominator, which is 1 plus I, to eliminate the imaginary part. This will result in a rational denominator. 3 plus 2i, times 1 plus I, 1 minus I, times 1 plus I. Now, we can simplify the numerator and denominator separately. Numerator, 3 plus 2i, times 1 plus I, equals 3 plus 2i, plus 3 plus 2i. I equals 3 plus 2i plus 3i plus 2i2. Since I2 equals minus 1, we can rewrite the numerator as 3 plus 2i plus 3i2 equals 1 plus 5i. Denominator, 1 minus I, times 1 plus I, equals 1i2 equals 1 plus 1 equals 2. Now, we can rewrite the division problem as 1 plus 5i. 2. To simplify this, we can divide both the real and imaginary parts by 2, 1 half, plus 5 halves. This is our final answer.